Humanoid robots have moved out of the laboratory and onto active factory floors, performing real-world tasks alongside human workers. To manage this, Nvidia recently announced Halos for robotics. This functions as a safety operating system for the microenvironment, designed specifically to prevent collisions in close-quarters collaboration. Repurposing autonomous vehicle data, the system detects a person's proximity and stops its momentum in milliseconds, preventing the machine from striking a human. While this engineering feat secures the warehouse floor, it only addresses the immediate surroundings. It leaves a massive safety void when we consider the scale of fleet-wide deployments. Zooming out from a single warehouse to the macro environment, we face the reality of millions of autonomous humanoids entering the global workforce at once. Here, we find a mathematical mismatch. AI agents can execute physical and economic decisions in milliseconds, but the legacy infrastructure they rely on was built for a much slower world. In the global supply chain, for example, physical movement and financial settlement often rely on lags of 60 to 90 days. We see the same latency in the power grid. Current electrical infrastructure relies on slow, localized load balancing that cannot react to the instant energy draws required by large robotic fleets. Attempting to run millisecond physical AI on top of these asynchronous systems will trigger a systemic flash crash. The speed of the intelligence will literally break the physical and economic capacity of its environment. Managing this macro environment requires a different layer of infrastructure. This is the role of the ZYRO HIVE economic operating system. The system uses T+0 synchronization, collapsing the execution of a task and its economic settlement into the exact same millisecond. This forces the robot's speed to match the real-time availability of banking, data, and power, physically tethering it to the grid. By removing the time delay, we eliminate the lag that causes flash crashes, making high-speed fleet operations mathematically safe. The architecture also anchors robotic execution to a geohash, a specific digitized physical location. This creates a thermodynamic boundary. The fleet's actions are restricted by the limits of the specific local power grid where the robots operate. The system embeds a social boundary called me plus we. If an action lacks 67% cultural consent, the architecture physically rejects the command. When an AI agent attempts to breach these limits, the system instantly recalculates and reroutes the signal. This makes rogue systemic actions impossible, as the machine's capabilities are subordinated to the survival mandate of the living community. As edge AI and humanoid fleets scale, the silos between our digital, physical, and social worlds are dissolving. This shift requires us to rethink what safety actually means. It involves much more than avoiding a collision on a warehouse floor. True safety means energy grids that remain stable under pressure, supply chains that flow without trapped risk, and social boundaries that are fiercely protected. While foundational tech leaders have secured the microenvironment, it is now up to vanguard entities to synchronize the macroenvironment. This represents the evolution from artificial intelligence to intelligence augmentation, technology grounded in real-time thermodynamic and social truth. With millions of humanoids preparing to enter the workforce, we have to ask, are our infrastructure and our culture truly prepared for the speed of the demands they will bring?